All right. Greetings, everyone. I'm Carter Frost. I'm your SI for CS-11, Introduction to C++. And so today we're going to be going over the three CZs. It used to just be three C's, but now there's the Z. So making sure that everyone can get that is able to access Canvas, is able to do the things on Canvas. They're able to compile their code um, either on the replit or on their own system, and then also that they're able to get into zyBooks and been able to do the activities. Then we'll do we'll go just a little bit over bits of history, just so we can get a little bit of an appreciation of how far computing has come, and then we'll discuss the various different parts of main. And then if anyone had any requests for additional stuff that they would want me to cover today, I'm also happy to do that. So you can either unmute yourself or just put it in the chat, and I'll try to address that, whatever it is. So can both of you have both of you been able to log into Canvas, and you've taken the week 1 quizzes and engaged in the dialogues and all that? Or is anyone having any issues with Canvas? Okay. How about you, Sam? Okay, cool. Okay, so sweet. So that's good. And then both of you can compile either on the replit or on your own personal systems. Okay. And was that comfortable for you? Was that process on replit okay for you? Cool. And then how would you, Sam? Are you able to compile either on replit or on your own system? Cool. Okay. Sweet. And then I guess zyBooks, I've been able to log into that and do some of the activities. Okay. Okay, cool, sweet. That's fantastic. Those are major hurdles for a lot of students. So that's great. So I guess we'll just jump into a little bit of history, just so we can get a little bit of appreciation of how we've gotten here. So I'd like to talk about first about somebody by the name of Ada Lovelace. I actually have a robot here I can show in other sessions, named after Lovelace, and she was actually a mathematician. She's known for writing the first algorithm for any kind of machine before machines existed, that could really change their behavior based on actions. She came up with the idea that, well, maybe you have a machine that you have different levers, that then changes the state of the sort of the output and the behavior of that machine, and wrote up essentially a language that you could then program that machine in. And so she's regarded as the first computer programmer because of that. The next person I like to talk about is Grace Murray Hopper. She's a computer scientist. She invented the first compiler, and in the next slide I'll show you what when we compile something, what is actually happening. So I'll show you that, and we're very thankful that she figured that out, because I certainly couldn't figure it out, because it's pretty difficult. And then she also came up with the idea of machine independent programming. Originally, when you program something, it would only work on that one machine. Even if you had a machine that was practically identical, like it had the same, it was it was the same, like 3-story size building made by the same manufacturer. There were subtle differences between each and every computer, just because of how they were built. And so the problem was that if you wrote a program that worked on one of them, it wouldn't work on the other one. So Grace came up with the idea that you could have a programming language that you could program at once, and that it would run on multiple different machines. And we take that for granted, very much so. I mean, you think of an Android or an iOS app, there's all these different kinds of smartphones, but this app still works on all of these different devices. I mean, there's thousands of Android devices, and somebody just has to write one little small Java program, and then it works on all these thousands of different kinds of Android devices. So we take that for granted, but that's a huge as a huge hurdle in computing. And then she's also the first programmer of the Harvard Mark I computer. And the reason why that's significant is they spent millions of dollars back then, but now that would be equivalent to billions of dollars building this massive computer, but no one could figure out how to make it do anything besides just like basic addition. And it was supposed to be like calculating like missile trajectories and things. And so no one could figure it out. They had built the computer, they had spent all this money, but it was practically useless for them. And so she came in and she was able to essentially write all the programming for it to make it do the job that it was supposed to do. So that I think just adds to her badassery of like how great she was, because she could come in and solve these problems. You know, people had built the computer, but they couldn't understand how to make it work. So she was able to come in and do that. So let's talk about number bases. And you might have to move my face out of the way if it's in the way, or just minimize it. So we and we talked about this in class earlier too. Was we're comfortable with this thing called base 10, or the decimal system, that within one digit, within one position, we can express 10 different things. We can express the numbers 0 through 9. That's 10 different things, base 10. So the base is an indication of how many things you can express within one digit location. And so there's other number bases. So you've probably heard binary, which is base 2. It means that you can only express 2 different things within one digit. And we already know what that is. It's a 0 and a 1, or a true and a false, depending on who you talk to. And so computers use base 2. Pretty much all computers use base 2. I mean, there are a few exceptions. And so everything is either stored as an on or off state. We're able to take base 2 and we're sort of able to compress it into a way that's easier for our eyes, that we call hex. And the reason hex is great is because we can take 4 digits in binary in base 2. Like if we look down here, actually let me turn on the pointer, here we go. We can take the biggest value that we can express with 4 digits, 1, 1, 1, 1, 1, which is 15 in base 10. And we can express that as a single digit in base 16, or a hex, and that's F. And so we can express, if we have 4 bits, essentially 4 bits in binary, we can express, you can express everything from 0 to the number essentially 15 with 4 bits. But with base 16, you only need 1 digit to express the numbers 0 through 15. So it's just easier for your eyes to be able to look at that compressed, all that compressed stuff. And so, and we'll see on the next slide that like if there was an off by 1 error, like if somebody had one of these bits were flipped somewhere, that you would be able to see it with hex or base 16 much easier. So that's it, and you may have seen that for like colors when you're doing it in colors on like the color wheels online, where you like move your little cursor to like click which color of something that you want. Those values that it displays right below it, that's in hex, because you're able to express billions of different colors within this small 16 or 6 digits of base 16, so 6 digits of hex colors. You're able to express all these different colors. There was such a thing as a base 3 computer, or a ternary computer. The Russians built it during the Cold War. The problem was that it was so different from just how we think about computing, that no one really could sort of get it to work. More so than the traditional computer. It had more capability in the sense that you could do more with these 3 different states, but it was just so different that they weren't able to exert enough effort into fixing and making it work properly. So we don't consider, I mean, it's not around anymore, but just something fun that you can have computers that operate at different bases, but it requires different components and such. Does anyone have any questions about number bases? Okie dokie. Well, moving on then. So then let's look at what Grace Hopper gave us, which was the compiler. So the idea being is that we can take something that's human readable. So if we look on this right side, these are different languages or environments that can essentially get compiled in some way. Mostly the C++ that we're going to be working with here. When we've seen this already, the cout hello world. This line here, what a compiler does is it converts that into something that the computer can understand, the machine can understand. And so there's this level, it converts it into assembly code, and then from assembly code into machine code. And so here is just the program, you know, the int main cout hello world, and that's it. This one line with that wrapper gets compiled into this here, and this I expressed in base 16 because it's easier on our eyes. So imagine now that instead of an O, I was off by one letter. What would happen here is that we would see that one of these values gets changed. And when you work with a processor, like if that's your bread and butter, then you look at these blocks of hex all the time. And so being able to pick out one thing that's flipped, like, oh, this is a D when it should be an E, for a mistake, becomes much easier. As opposed to if I converted this, I guess we could call it a paragraph. If I converted this into binary, the ones and zeros that are actually stored on the computer, it would take up 3 pages of just like slides of just numbers, because I'm able to compress essentially, for every 4 of those bits, I'm able to express into a single digit into hex. We're able to make it much smaller. So like if we took just this first one, here, we see at the bottom, if I just take that first piece and then express it as binary, notice it takes much more space. So now imagine that, each of the four digits of hex, if I expanded them that way. So it's very nice that compilers in different programming languages do this, where they're able to take things that are somewhat human readable for us and convert them into something that the machine can understand. Very few people have to be able to look at this and understand what's going on. We have like the last class at Cabreo, for very brief time, you have to be able to like look at this piece and then understand what that means per a processor. And we work on the same processor that's on the PlayStation 1. But it's very specific to each computer in each processor what these mean on the computer. So this is actually for my laptop. This wouldn't run on a smartphone, for example, but this cout hello world would. So that's the whole idea, is that you can take this this that was coded once by the human, and you can compile it to run on multiple different machines, and that the machine code, this stuff, looks different per each computer. So I'm very thankful that somebody much more brilliant than I came up with how to make the compiler do this, and a lot of cool tricks to help solve these problems. And so you don't need to know this. This is just something that you can sort of put into your gut and have an idea and an appreciation for a lot of work that's been done in advance for us. And if this is the kind of thing that you enjoy, if you enjoy looking at all these hex values, there's a lot of money for you, because that's a very niche career. Okay. All right. So yeah, computers used to look like this. People used to spend many thousands of dollars to get a computer that, if they could get blinking light after months of work on it, that they considered themselves very successful. There's these things called punch cards. They were physical pieces of paper that you had to put holes in for your program. So first you would write your program on like a piece of paper, and then you would then translate your what you wrote into this, into sort of these ones and zeros down here into this binary, and then you physically had to put holes in paper and then feed these sheets of paper in the correct order into the machine, and hope that the machine didn't actually grab it and shred it in, or something bad happened to it, or that you fed it in the wrong order or something. You had to feed everything in properly in the right order, and then your program would run, and then it might give you a little printout, and you'd be like, oh, success, the printout looks good. Many times, a machine eats the card, and then you're like, oh, well, I have to go figure out what was on that card and then recreate it, or if you fed them in wrong, you could crash the entire computer. And sometimes crashing the computer, like best case scenario, would only take the computer down for about 5 hours. But like in some scenarios, you would take the computer down for several days because it physically damaged a part of the computer, and somebody would have to go in and replace a piece of the computer. So that doesn't happen. If somebody writes a bad program nowadays, maybe you get a blue screen of death and maybe your computer crashes, but ultimately, and that's only like in extreme cases. Most time when you get like the page is not responding or whatever, you can just close it and then reopen it, right? And we can thank Anita Borg for that. So Anita Borg, she's a computer scientist. She came up with the idea of a fault-tolerant Unix-based operating system. So Unix is essentially the foundation of everything that is not Windows. Windows has is a fake Unix part of it, but all Linux, all Mac, your microwave, your toaster, Android, iOS, almost every computer that we can think of besides a Windows computer is based on Unix, or is Unix based. And the idea of fault tolerant means that the computer literally doesn't catch fire, that something bad can happen within a program, and it's not going to take down the whole computer, and because that used to be the case. And then she also developed the idea of mass emailing. Originally, emailing used to just be a one-to-one thing. With the ARPANET is that you would be one person and you would send to one other person, and that was it. So Anita Borg came up with the idea that one person could send out to multiple people. And so we can thank her for all those spam emails and whatnot, but also things like this class wouldn't be feasible if the instructor had to like stop and send an email to each individual student. And then if they reply, then there's all these different replies. So it's super useful to have this kind of communication model where you have one central person that sends out stuff to multiple people. She was also the chief researcher at Xerox PARC. And the reason why that's important is that's where Apple and Microsoft both got a lot of their ideas. So for example, the Ethernet cord and also the protocol. Let's see, so the Ethernet cord, if you can see, it's this cord here. You can see in the camera. It's that standard internet cord that we associate with, but also the protocol, how the ones and zeros are organized that go down into the wires. That's also called Ethernet. So she was the chief researcher on that, and then also something that we also take for granted, the mouse, that clicky thing. She was also the chief researcher on the mouse, and the idea that you could have this pointer that you can click on things in the display. So huge, yeah, that's huge. Computing would not be recognizable if it wasn't for that. She also founded the Institute for Women in Technology. And the last person I like to talk about is Margaret Hamilton. She's actually still around. She does consulting for various different coding projects. That picture right there is actually her team's handwritten code for the Apollo guidance computer, or the EGC. And so, I mean, that's a lot of code, right? Imagine, I mean, like most people will groan if they have to handwrite, a single piece of paper of code. And that's many thousands of sheets of paper. So she was the lead developer for the Apollo flight software. And it was really her foresight for errors, for being able to think of like what could possibly fail. Right? If this sensor was mounted improperly, or if the sensor stopped working, or the sensor was reporting bad data, or whatever, what is the best thing to do in those situations? And in advance writing code, um, it's really important to think to sort of just have that in mind if you're a computer scientist or an engineer or whatever, that always think about what could happen or how could my stuff be misused or accidentally used, um, and how will my stuff uh, handle those situations. So if you're building a bridge, right, you don't want to build a bridge that if somebody walks up to it and pulls out a single bolt, that the whole bridge collapses, right? It might be malicious, or it might be, you know, a kid just playing around and, you know, pokes the bolt and the bolt falls out. So it's important to think about how things can fail and how you can write or build things so that it's robust against failing. And right now we don't know any ways of coding that, but that's just something to be, you know, have in the back of your head as you're writing more and more complicated programming, is what could possibly happen or how could this possibly fail. And even if you don't know how to solve that right then, leaving a note or some kind of documentation behind saying that this could fail in this way can be very useful if for yourself and for other people if they're going and looking at your code and trying to figure out how it failed to be able to fix it later on. She also wrote Project Sage. Project Sage was originally for detecting missile launches. This was before we had seismometers to be able to detect like the micro earthquakes. Originally, it was, you know, looking at satellite and radar views to detect missile launches. What's funny is that now we have this technology to detect, you know, the tremors, and then we use that for detecting missiles. We actually use Project Sage still today for predicting weather. So most weather predictions that you see are actually from this, you know, over 50-year-old code that Margaret wrote for us. So if you ever wonder why, you know, why maybe the weather predictions aren't super duper accurate, just keep in mind that the code that's doing that prediction is over 50 years old and it's still mostly correct. So gotta be thankful for that. Yeah, so those are the 4 people I like talking about. Any questions about those individuals? Pretty cool people. Uh, would encourage you to read up a little bit more about them, because they've definitely, I mean, this is just a small little snippet of the things that I've gleaned about reading about them that I thought was important to share. Okay, so documentation. So documentation is really, really important. And there are some instructors that will straight up just fail you if you don't properly document your code. But mostly you should be documenting for yourself, because what happens over time is you forget. There are many times when I write up a ton of code, and then I come back to it 2 weeks or a month or sometimes even years later and try to pick up the project, and I have no idea where I left off, what's broken, or my suspicions for what could be broken, or whatnot. So we forget. Also, sometimes we need to explain what we're doing. Maybe we're doing something, you know, maybe we're multiplying by some random number because that makes everything work. Maybe explaining what that number does and what the significance of that is. Even if you don't understand what it is, you can just be like, yeah, I put in this, you know, your documentation could be like, I put in this magical number, I don't know why it works. That's still useful, because now somebody could go into your code and be like, aha, that's actually really close to pi, and that's why you're able to calculate how the wheel, you know, how the wheel odometry on the rover is working properly. And so they're able to go in and just actually put in the number pi, and then they're able to fix some issues that might have been occurring, because you put in the number 3 and you're like, well, it seems to work pretty well. So documentation is really important for stuff like that, for yourself when you come back to a project, to explain to other people what you're doing, and also to explain to help people understand what's going on that may be coming in to fix your code later. There are many times when people will write code once, and then maybe they'll leave the company, or maybe they were contracted to write that code, and then years later they say, oh well, we want to add a feature to that code, and then they hire that person back, they contract you back to come in, and they'll be like, oh, $20,000 if you can add this feature. And if you did a really good job of documenting, you could be done in 2 hours. You could get $20,000 for 2 hours of work. But there are other times when I've seen people where they're brought back in and they didn't leave documentation and they don't understand where they left off or why they were doing some things, and they essentially had to rewrite something from scratch, and that took them a year or two to work on. And that's a lot of, I mean, $20,000 is a lot of money, but when you're working, a year or two, when you could be making $100,000 on fixing something that if you had just left documentation when you originally wrote it. So that's sort of that trade-off, is that you might encounter your code again, but also other people might be working with your code. And if you left really good documentation, they're going to be very thankful. And it has a really weird way of coming back at you sometimes. I've interacted with people at big conferences with 30,000 people up in San Francisco. That's not going to be happening anytime soon. But these big conferences, and people are talking about coders like, oh yeah, don't hire him, he doesn't leave comments, or yeah, hire them, they leave really good, really useful comments. Now that's actually a metric that maybe you don't even know when you apply for a job, but people are talking about each other, especially if they're known within these niche markets. So being a good steward of your code, leaving documentation is really, really important. I cannot instill that enough. And so in C++, we have two different ways of leaving comments. We have this inline comment here that you've already seen Ed use, and then you've also seen this block comment that you've also seen Ed use. The inline comment you tend to use in the same line as the code to explain what that one line is doing, versus a block comment is you're trying to explain a block of code, or so typically you'll have one of these at the top of your code of your program, of each file, and that block comment would explain everything about the file and what's going on, who wrote it, those kinds of things. But also if you have a block of code that you want to explain what that block is doing, what that gobble of code is doing, that and it may just be like 4 lines or maybe 20 lines. If you want to explain what that area of code is doing, you would use a block comment. And that allows you to have multiple lines where maybe you have a paragraph. A lot of times what I'll do is when I'm giving an assignment or work to do, and I have like a paragraph describing what I need to do, I'll copy and paste that into my block comment. And then while I'm coding, I can look right above and make sure that what I'm coding directly corresponds to what my code needs to do in that comment. So that's always really good advice, is that whenever you're working on something that you already know what it needs to do, what the end result is, copy and paste that and use that as a comment, because somebody has already written it for you. Then you don't have to write that as a comment. And hopefully, and if that doesn't make any sense now, it probably will in about 3 weeks. So let me know. But yeah, document. Anything you don't understand, or you think that could confuse people in the future, leave a document, leave a comment for them, including yourself. Okie dokie. Let's talk about main. So we've probably seen these both of these, within the scope of C++. And for probably the first half of this semester, it's not going to matter which one you use. So let's first talk about this first piece here, this int. So this int, or integer or whole number, you tend to see that in the body of main, that we always say return 0. And what happens is that that's being given back to the operating system. Main is a keyword. Most programming languages use it, and so the operating system knows to always go and look for something called main, which is why if you accidentally change this to like an uppercase main, that you're going to get, when you try to compile, it'll compile fine, but when you try to run the program, you're not able to run the program. It's always looking for this this normal main. So this return 0, the 0 means that things is completed successfully. Anything that's non-zero means some kind of error occurred. And in a document, you would specify what the numbers mean. So you might use negative numbers to mean that the user, when they were running the program, did something that caused the program to fail. Then you might use positive numbers to indicate that something about the system, maybe they're missing a graphics card or whatever it might be. And you would leave a document. You would say, oh yeah, the number 5 means that the file doesn't exist, and the number 4 means that this component is missing, or whatever that might be. So 0. So for the scope of this class, we'll just be returning 0 always. But know that you can return something that's non-zero, and that will indicate some kind of error. Then you see this main part with these curly braces, and these curly braces are essentially how we group parts of code together. So you can say, like where it says body, you can have a ton of code within this body if it's surrounded by these curly braces, and that helps specify that all of these things belong to this thing called main. If you omitted these, then the code that you put in there has no way of knowing who it belongs to if you have more than one line. So you should always have curly braces. Even if you only have one line like hello world, you should still have curly braces because that makes it very clear when people are reading your code and for yourself. A lot of times people will have these one-liners where they omit the curly braces. And the problem is that then when they go to test things, maybe they add an extra printout. Now they have 2 lines because they have the code and they have a printout, and they forgot the curly braces. And now one line works, but then the other line doesn't. So always use curly boys, just in general. It makes your life much easier. And then we see these parameters or arguments here in some cases. We're not going to use those until much later into the semester, but just so you can get sort of a sampling of what they are. This argc is the count of arguments. It's the number of things that were given when you run a program. So if you run a program, if I say, test blah blah, these blah blahs are arguments. This is extra data that I give to it. Or like we, for example, when we did ls-la or whatever, when we wanted to see the things that were in our directory. Maybe I should zoom that in. That this ls is the name of the program, very much like how we did like .a.out or .a.exe if you're on Windows or whatnot. That if you give extra things, test 1, 2, 3, that these here are all arguments. This is extra stuff that you're giving to your program. And we're not going to need to know how to do any of that until halfway through the semester, so that's okay. But just know that argc, so there's 5 of these arguments. There's 5 things. There's test 1, 2, 3, and things that have spaces are considered separate things. So yeah, so that's what argc is going to be. And then this char, star, args-v, and square brackets, just think of it as that's all of the arguments. That's all of that. That's all of it's sort of like a string of all of the things that were given to you. And again, we're not going to be dealing with that until much later. Any questions about main? Yeah, so I think that's pretty much it. So yes, let's take a look at the zyBooks. So what was the question?
It's from challenge activity 2.8.
Yeah, so I guess was there a question about it, or did you just want help with that particular one?
Yeah, like, can I share my screen real quick?
Sure. Go for it. With some. Okay, so I'm going to spoil you guys with some extra bits too. So bonus bits. So now we're familiar with traditional bits, with the 0 and the 1 bits. But we live in a really cool time when we now have these quantum bits. And the first quantum bit that I like to talk about is a p-bit. And a p-bit is everything between 0 and 1. And how many different values do we have there? Right, how many different values can we express between a 0 and a 1? Between 0 and 1. So like 0.5 and 0.4999 and 0.1. So it's an infinite number of values, right? There's an infinite number of decimals or fractions that exist between 0 and 1. With a traditional bit, yeah, we only have two values that we can express, a 0 or 1. With a p-bit, we have an infinite number of values. So now imagine that you have a single p-bit and you can store your entire musical library inside of it. Pretty nifty. And then there's these things that you probably see about on the news all the time called qubits. And they're much sexier things, because not only is it everything between 0 and 1, but it's actually any position on a sphere. So in polar coordinates, that's 3 infinity. And then there's a distance from the center. So that's another infinity. So that's 4 infinity. And then it's a vector, which you can think of like as an arrow, and that points anywhere along the surface. So that's another 3 infinity. So you've got like 7 infinity or 8 infinity, which is still infinity last time I checked, of data that you can store within a single bit, within the single qubit. And the nifty thing is that you can entangle these qubits. You can essentially take one qubit and connect it to another qubit. So anything that this qubit does here. So imagine that you have your bestie has a qubit along with you, and any music that you put into your qubit will pop out on the other qubit. And the idea being is that you could be any distance, from any practical distance from each other. So maybe somebody's down spelunking in a cave where traditional radio wouldn't work, but you had these two entangled qubits. You could suddenly use it like a walkie-talkie of infinite amounts of data back and forth, or Mars and Earth. These things that may not be practical for traditional communications, you could entangle the qubits. One of the issues, though, with the qubits is that they're not stable for long periods of time, because they have to stay super chilled, because the way that they're stored is in these superconductors, which require very, very cold refrigerations. So that's a problem that hopefully engineers are going to solve within our lifetime. And then we'll be able to have these qubits that have practically an infinite amount of data that they can store, but also that you can share those qubits with other people. You can entangle them with other people, and then be able to transmit enormous amounts of data back and forth without the need for fiber lines in the ground, or radio waves or any of that kind of stuff. So really nifty stuff that's coming up in our future. And there's also lots and lots of quantum computers being built. I mean, Google and the government, they own thousands and thousands of quantum computers. While they tell us that they practically don't do anything useful, who knows? IBM does have a quantum computer that you can go online and use and play around with it. It's a very simplistic thing where you can like flip qubits and see how they interact with other things. So that's always a fun exercise to do. And that's all I've got for today. And I think it's pretty much time to jump into class. But if anyone has any questions before we hop over, let me know.